All right, let's dive into one of the weirdest forces in the entire universe. We're talking about a real physical push that seems to come from, well, absolutely nothing. It sounds like something straight out of science fiction, but I promise you it's very, very real quantum physics.
So let me just ask you this. Can empty space push things? It feels like the answer should be no way, right? I mean, how can nothing actually exert a force on something? And yet, that exact question is what opens the door to one of the most bizarre phenomenon in all of physics.
To really get our heads around this, we have to completely change what we think of when we say the word nothing. Because, when you get down to the quantum level, empty space is anything but empty.
So let's rewind the clock a bit to 1948. A Dutch physicist named Henrik Casimir comes up with this incredible prediction. He theorized that if you take two metal plates with no electrical charge and put them super close together inside a perfect vacuum, they'd actually be pushed toward each other. And the thing doing the pushing? Not gravity, not magnetism, but the vacuum itself. And this, my friends, became known as the Casimir effect. The core idea is that empty space is just constantly fizzing with these things called quantum fluctuations, these tiny fleeting bursts of energy that pop in and out of existence. When you put objects like our metal plates into that space, you actually change those fluctuations, and that creates a real measurable force. Okay, here's a pretty good way to picture it. Imagine that vacuum of space is like a huge, chaotic ocean, just full of waves of every single size you can imagine. Now our two plates, they're like two harbor walls. Outside of those walls, all the waves are just crashing around like crazy. But in the tiny gap between them, only very specific waves can actually fit. So what happens? You end up with more wave pressure on the outside pushing in than on the inside pushing out. And boom, the plates get squeezed together. And get this is not just some neat thought experiment. Oh no, the Casimir effect has actually been measured, and our best experiments confirm it exists with about 1% precision. This thing is real. So, if we know this force is real, here's where the fun really begins. What happens if we start, messing with the fundamental rules of the universe? What if we could actually change the very fabric of the space that this force is acting in? Well, this is the exact rabbit hole a 2022 paper in the journal Physica E went down. These physicists asked a really profound question. If we change the mathematical description of that space between the plates, does the Casimir force itself change along with it? They decided to test this with two totally different what-if scenarios. First, what if we tweak the rules of physics? And second, what if we change the actual shape of the space itself? Okay, so let's tackle that first one, the fractional approach. You can think of this as putting a kind of dimmer switch on the laws of physics. We usually think of dimensions in whole numbers, 1D, 2D, 3D, simple. But fractional calculus lets physicists explore what might happen in, say, 2.5 dimensions. It's not about creating some new physical place to visit, but about changing the mathematical rules of how things interact. It really is like turning a smooth dial instead of just flipping a switch. Now, as the paper itself points out, this gets mathematically tricky really fast. But the key takeaway is right there at the end of the sentence. The energy and the pressure are only slightly affected. So as they turned that dial of the fractional order, the force did change a little bit, but not by a whole lot. It was always an attractive force, just a tiny bit stronger or a tiny bit weaker. A very subtle tweak, all things considered. But their second approach, whoa, this one was way more dramatic. Instead of just tweaking the rules of physics, what if they could reshape the very fabric of space itself? This time, they made the space between the plates fractal. Think about a coastline on a map. The closer you zoom in, the more jagged and complex and detailed it becomes, right? That's a fractal. They mathematically made the space between the plates rough and complex, just like a coastline or a snowflake. And you know what? When they did this, the math suddenly became much more straightforward. The energy was now directly related to the square of that fractal dimension. No more super complex functions, just a simple, really powerful relationship. And the results were just dramatic. Take a look at this chart. A bigger negative number here means a stronger attractive force. So notice, as the fractal dimension, alpha, gets higher and closer to a nice, smooth 1, that attractive force gets way stronger. At an alpha of 0.9, you get a powerful energy of negative 1.88. But as the space gets rougher and more fractal, dropping down to 0.25, the force weakens a lot. Whoops, let me rephrase that. The crucial point is that as the space between the plates gets smoother and the fractal dimension gets bigger, the attractive force gets much, much stronger. The geometry of the space has a massive impact on the physical force.
So, what's the big takeaway from all this? What happens when we compare these two approaches side by side? It tells us something really profound about the link between the math we use and the reality we actually observe. Let's just break it down. Changing the rules of physics with fractional calculus, that led to some really complex math and, in the end, only a small change to the force. But changing the shape of space using fractal geometry, that was mathematically more direct and had a huge, huge impact on the force.
And the paper's own conclusion backs this all up. They say the energy is improved for lower fractal dimensions. Now, in this context, improved means the energy value becomes less negative. So that confirms it. A rougher, more fractal space leads to a weaker attractive force. The actual geometry of reality is an incredibly powerful lever.
So what this all boils down to is something pretty mind-bending. The physical reality we measure isn't totally separate from the mathematical tools we use to describe it. By changing the mathematical assumptions, the very language of our description, we fundamentally change the outcome we see. The map, in a very real sense, can alter the territory. And that leaves us with this one final, profound question. If just changing our mathematical model can reveal completely new physical behaviors, what other fundamental forces, what other versions of reality are just sitting out there, waiting for us to find the right language to finally see them?